The Earth as seen from space on Boxing Day 2004. Indonesia, the world's largest island nation, where the Indian Ocean meets the Pacific. It's 8 o'clock on Sunday morning. Across the main islands of Sumatra, Java, Kalimantan, Sulawesi and Papua, and on the 6,000 smaller islands, over 200 million people are going about their daily business like they do every Sunday morning. It's the same picture in Banda Aceh, a coastal city of 260,000 people at the northern tip of Sumatra. Nobody has the slightest idea what happened just a few minutes ago, 100 miles out to sea. At 7:59, one of the most violent earthquakes in history shook the ocean floor and triggered a giant tidal wave, a tsunami. The people of Banda Aceh and its neighboring village, Lona, are blissfully unaware. Until a 15-meter wall of water crashes onto the coastline, even bursting over a 30-meter high ridge further inland. It leaves a scene of utter devastation in its wake. Satellite images show Lona before and after the tsunami hit. A few seconds later, the wave reaches Banda Aceh. In minutes, 60,000 people are dead. Most of the city is wiped off the map. Experts will later use satellite data to map the full scale of the tsunami's destructive impact on the region. And the question will be asked, shouldn't we have been able to prevent this catastrophe? Tsunamis are very rare events. Usually they are triggered by seaquakes, earthquakes that take place deep beneath the sea. But not every seismic tremor on the sea floor causes a tsunami. This map lists the major seaquakes of the last 35 years. White dots show quakes with a magnitude of 5.5 on the Richter scale, red dots those of 7. And still, out of the hundreds of these powerful tremors, only a few caused tsunamis, 1 every 3 years on average. The Indonesian archipelago is a high-risk earthquake region. Satellite images reveal the mountains and valleys of the ocean floor and show us what the naked eye cannot see. These massive earthquakes originate along a fault line where the land abruptly drops to a great depth. Off the west coast of Sumatra, for example, the seabed falls away dramatically to a depth of more than 20,000 feet. Two giant plates of the Earth's crust meet here. The Australian plate is being slowly, relentlessly forced under the Eurasian plate. Deep in the Sunda Trench, these plate mechanics are more clearly demonstrated as the deep seafloor powerfully pushes against the base of the island landmass, gradually lifting the Indonesian archipelago above it. Over long periods of time, the landmass is squeezed and squeezed until it rebounds with a jerk, resulting in a sudden tremor, a giant underwater quake. Seismic stations accurately monitor even the smallest events, but a tsunami cannot be reliably predicted from this information alone. This is where the German-Indonesian early warning system InaTEWS comes into play. In the event of an earthquake, dozens of land-based sensors report the tremor back to the operations headquarters in the capital Jakarta, and time, magnitude and location of the quake are immediately calculated. At the same time, GPS stations monitor how soil on the land has changed shape and moved about due to the quake. By using navigation satellites, tiny shifts in the Earth's crust down to just a few centimeters can be observed regardless of weather and daylight. These two sources of data, the seismic alerts and the GPS measurements, serve as an alarm clock for a complex system that is automatically set in motion. From this point on, every second counts. Soon, more and more data arrives at the operations headquarters. The system immediately starts running all the available data through models from its archive. Thousands of scenarios have been pre-rendered to save time, taking into account the topography of the ocean bed, the surface structure of the sea floor, and the depth of the epicenter. Within seconds, the software identifies one scenario that best correlates with the data that's coming in, and then calculates if a major tsunami is heading for the coast or if it isn't. But is this information on its own enough to raise the alarm? Every false warning would be fatal, as people would start to mistrust warnings in the future. But raising the alarm too late wouldn't give enough time for the rescue plan to be put into operation. The clock is still ticking, but there isn't yet enough evidence for a tsunami warning. The officer on duty has to make a decision. He needs nerves of steel and must wait a few moments longer, even as the system's calculations are now predicting a 3-meter high wave approaching the west coast of Sumatra. The computer simulation clearly shows the wave coming closer. The system is now working flat out. Underwater, the seaquake's shock wave travels away from the epicenter at speeds of up to 600 kilometers an hour, and it soon hits one of the pressure sensors tethered to the bottom of the sea. The sensor instantly reports the shock to a nearby buoy on the surface, which has sensed the tsunami wave at the same time. The buoy measures a lengthened, stretched wave peak. This is the key marker for initiating the wake-up procedure and raising the alarm. These measurements are fed into the early warning system via a telecommunications satellite high above Asia. The seconds go by. Finally, the information from the buoy arrives at headquarters and confirms the predicted tsunami. The officer on duty could set off the alarm now, but he still wants to look at one more set of data that is coming in from gauge sensors positioned on small offshore islands. One indication of an approaching tsunami would be a sudden drop in sea level at the coast, moments before the giant wave arrives. The gauge sensors will feed this vital conclusive information back into the system. When the gauge sensors activate, and when the waterline briefly drops by more than 2 meters, the picture is complete. Every measurement refines the forecast. Meanwhile, the system is predicting a tsunami wave of 5 meters, more than 15 feet. Just a few minutes have passed since the tremor at the sea floor. Now the gauge sensors show the typical pattern of a major tsunami. This is the long-awaited confirmation of the computer projection. With all this information to hand, a false alarm is now out of the question. At last, the chief officer on duty can take action. A glance at the monitor. The system recommends the immediate evacuation of the coastal area around the city of Padang. The chief officer presses the alarm button. On the basis of all available information, he can be confident. This is no hoax warning. The tsunami will come. Seconds later, the residents of the affected area receive a warning by SMS. The media are informed by ticker and fax, and they broadcast the breaking news. Horns sound on the beaches. For those who take immediate action, there is still time to get to safety before the tsunami hits. 250,000 people lost their lives in the 2004 Christmas tsunami. We won't be able to stop tsunamis from happening in the future, but with the help of state-of-the-art early warning systems, we can alert people early enough and reliably enough. We can save lives.